Welcome children for the next episode about the magnetic effect of electric current. In our previous class, we discussed about the heating effect of electric current. That means when current is passed through a resistor, electrical energy there changes to heat energy. That means there we discussed about heating effect of electric current, and from that we got the relation H is equal to I square RT, and also we discussed about what is actually electric current. It is the rate of flow of electric charge or charge flowing across a cross section in unit time. Then electric potential difference. It is the work done to move a unit positive charge or unit charge from one point to another point. That is the electric potential difference. So there we discussed about the heating. Now we want to discuss about some other effect of electric current. Among that, one is magnetic effect of electric current. What is the magnetic effect of electric current? When current is passed through a conductor, is that a current can produce magnetic field. For that, here is given on activity. In that activity, a cardboard and a straight thick wire is passed through this, and this wire is connected to a battery, then a plug key, then we can give to a variable resistor, and if you want to measure current, we can here we can give or connect an ammeter also. When current is passed through this on, that means before on this key, place a compass needle here. See a compass needle. This type of compass needle is small compass needle. This compass needle always shows, always it is in, see this is also a needle, compass needle. This always in north-south direction. Its direction is always in the north and south. Now, before we on the plug key, observe the direction of the needle. Then, on this plug key, then observe the direction of this magnetic compass. Now, you see a change in its direction. You see a change in its direction. Why? We know this magnetic needle is a small, this magnetic needle is a small bar magnet, but it can move freely. Here in this compass, it can move freely, and it always in the north-south direction. It always in the north-south direction. The end which point towards north is, we know, North Pole, and the end which direct towards south is the South Pole. And also we know like poles, that means north and north or south and south. These are the like these like poles, what actually do? These like poles repel each other. Like poles repels. But unlike poles, which are the unlike poles, north and south. Which are the unlike poles, north and south. They attract each other. That we know. Here, this magnetic compass that is directed in north and south direction. When we put key in this plug key, that means the circuit is on, current flows through this. Then what happened? This magnetic compass deflects. Why this compass deflected? Because they produce a magnetic field. Because here a magnetic field is produced. Here a magnetic field is produced around the current carrying this wire. So, due to the action of these two magnetic field, this compass deflected. Why this compass deflected? Or from the deflection of the compass, we can get an idea that there is a magnetic field produced when current flows through this wire or this conductor. So, from this, we get the idea that a magnetic field is producing around a current carrying conductor. And about this electromagnetism, that means a scientist, 19th century scientist, and his name is Hans Christian Easton. Hans Christian Easton. Hans Christian Easton, he observed the magnetic effect of electric current. That means he first observed about the properties of what is electromagnetism. During his observation, that means accidentally he got that idea. That means when a compass is placed near a current carrying conductor, that deflected. That idea he got accidentally, but later on he studied about this, and also he discussed and studied about more things like fiber optics and also working and nature of radio, television, etc. These are all his contribution. Contributions, that is Easton's contributions, belongs to what is more studies about radio, television and fiber optics, and also he first observed what about the magnetic effect of electric current. Now, we want to know more about magnetic field. We know there are two poles in a magnet. Which are they? They are north and south. For a bar magnet, if it can move freely, then this magnet directed towards north and south direction. The end which pointed towards north is called north and the other end is south. And also we know what like poles, which are the like poles, north and north or south and south. they repel each other. But what about the case of unlike poles? When we observe the case of unlike poles, they attract each other. Now here on activities 1. See, before that activity, here one question is given. Why does a compass needle get deflected when brought near a bar magnet? See question. Why does a compass needle get deflected when brought near a bar magnet? Actually, we know a bar magnet consists of two poles. Which are the poles? North and south. And also, a compass is also a small bar magnet. But the difference between these two is bar magnet that cannot move freely, but in the case of a compass like this, it can move freely. That means this compass can move freely. So this compass is also a bar magnet. Compass is also a bar magnet. So there, when like poles approach each other or comes near, they repel. But if there is unlike poles that attract, that is the reason they deflected. That is the reason why the compass is deflected when it brought near the bar magnet. Now another one activity is given. That means what is actually magnetic field and how that magnetic field is there. See, for that you are do one activity. Take a drawing sheet and fix it on a drawing board. Then place a bar magnet at its center. That means first you want to take a drawing board, then fix a white paper. That means a drawing sheet on it, then keep a bar magnet at its center. Then you can mark the region around this bar magnet. It's on the north and another on the south. Then sprinkle some iron fillings, iron dust over, that means this board around this bar magnet. That means sprinkle some iron fillings over this paper. After that, you tap this drawing board 1 or 2 times. Then you can see these iron fillings get arranged themselves. That means in a particular manner. That means that's arrangement is somewhat like this. That means near the poles, these iron fillings arranged more. And also we can observe some arrangement like this. That means some iron fillings moving or going from one pole to another in a car. That means it arranges like this car. That means it moves from one pole to another near the bar magnet. But at far distance we cannot see this arrangement. So the region or the space or the surface around the magnet where the magnetic property exists, is a magnetic property of the magnet exists around the magnet for a particular area, and that part is called magnetic field, and that part is called what is a magnetic field. So what is actually a magnetic field? Magnetic field is the region around the magnets where the magnetic property exists. But it's actually, it is the region or it is the space around a bar magnet or a magnet where the magnetic property exists, and it is called what is a magnetic field. Magnetic field. What is magnetic field? It is the region surrounded to the magnet where the magnetic property of this magnet exists, and it is the magnetic field. Now this magnetic field we want to. For that you want to one more experiment or activity. Here take a drawing board and fix a drawing sheet over it, then place bar magnet at its center, mark its north and south poles. Mark its north and south poles. Then bring a magnetic compass near its north pole. We know for a magnetic compass there are two poles, one north and south. And when we brought this end, one end pointed towards here and other end is opposite. Now both end will mark. Then move this compass to the point which we marked towards north. Again we place this compass over this, then again we mark this north here. Then move the compass above this dot and again mark the direction of north. And if we repeat in this manner, we can see that pole, that means that one is coming towards the south. When we join all this, we get one magnetic line of force. We get a magnetic line of force. See how we draw here a magnetic line of force. What are the methods or what are the steps we want to follow it? What are the material required for this means drawing sheet, drawing paper, then bar magnetic compass, then pencil. And the steps at first, a drawing sheet is fixed on a drawing board or a white paper fixed on a drawing board. Then keep a bar magnet at its center. Around the bar magnet we can give outline. Then mark the north and south. Then brought a compass near the north pole of this bar magnet. Then you can see its south end is pointing towards north, and the north point we marks. compass to this point, let's we mark it at the point north, then this process repeats, that comes to the south. So we get one magnetic line of force. Then in this way when we draw, we get another magnetic line of force. In this manner we can draw a number of magnetic line of force. That means we can draw a number of magnetic line of force. We can draw a number of magnetic line of force in this manner. See here, this magnetic line of force, we consider the direction in which North Pole moves. Conventionally, the direction of magnetic line of force is the direction in which North Pole moves. Conventionally, the direction of magnetic field is the direction in which North Pole moves. This North Pole moves from north to south. So, magnetic line of force originated from north and ends in south externally. That means outside, it starts from north and goes to the south, and inside the magnet it goes from south to north. So a magnetic line of force is a closed loop. A magnetic line of force is a closed loop, and it starts from north and it goes to south outside the magnet, but inside the magnet it goes from south to north. So a magnetic line of force is a closed loop. Here, see, near the poles, these magnetic lines of force are very close. Near the poles, these magnetic lines of force are very close. So, here the magnetic field strength is small. Here the magnetic field strength is small. So, the strength of the magnetic field is the, we can say as the degree of closeness of the magnetic lines of force. When the degree of closeness of magnetic lines of force is small, where we can observe it near the poles, there the strength of the magnet is small. So magnetic field strength is small where near the poles, where the degree of closeness of the magnetic lines of force are also more. So there the strength also more. And this magnetic field, see, it has both magnitude and direction. It has both magnitude and direction. Magnetic field that has got both magnitude and direction, and the direction which we take as the direction in which the North Pole moves. In which direction the North Pole moves, that is the direction of the magnetic field. See here, these magnetic lines of force here and in these areas are very close. So the strength also more. Now see, this magnetic field lines never intersect or cross each other. This one magnetic lines of force and this one another magnetic lines of force. These two never intersect. Why? If these lines intersect, at that point this compass will show. That means the direction of the compass at this point or the direction of North Pole should be in 2 two directions. If the lines of force intersect, then the point of intersection at which a magnetic compass shows two directions. Its north pole points in two direction, which is not happen. So these magnetic lines of force, what actually does not do, they does not intersect each other. That does not intersect each other. Now you got idea how you can draw magnetic field lines around a bar magnet. The different steps you want to follow how to draw magnetic field lines around a magnet, and that steps with that these magnetic field lines once again see how graphically or diagrammatically we can represent these magnetic field lines around a bar magnet. See, this is a bar magnet. If this is the north and this is the south, this magnetic lines originate from north and goes to south. That means arrow mark come out from north, and at the south it goes in, and inside it goes from south to north. In this way, you can draw number of lines of force by using compass. See the difference. Arrow mark at south, that is going into the magnet, but here you see at the north it is coming out. In this manner, you can represent magnetic lines of force around a magnet. Now, we want to discuss about how the magnetic field around a current carrying conductor. Magnetic field around a current carrying conductor. See, we arrange a thick copper wire in the north-south direction. Below it, a compass needle, which is, see, here is a compass needle. This also in north-south direction. That means at first we keep a compass. At first we keep a compass, and above we arrange a thick copper wire which is parallel to this compass, and it is in north-south direction. Got idea about how to arrange this? See, in this manner, here is a compass that is in north-south, and above this we want to arrange, that means if this compass is in north-south, above this we arrange a conducting wire parallel to this one. Now these are in the same direction. Now to this we can connect a battery and plug a key, and to a rheostat to regulate current. Now this compass is below this conductor, and it is parallel to this also. When current is passed from, see, current direction is this one. Now on the plug key, now current is passed through this. This compass needle now passing from north to south. Now you can see the north pole of this compass is shifting towards east or deflected towards east. So current from north to south, deflection of north pole is in east direction. In which direction it is deflected? It deflected to east direction. Now we rearrange this battery. See now. Now the current is from south to north. Now this deflected towards west. This deflected towards west. That means north pole of the compass now deflected to west. From this, what idea you can get? That means when the direction of current changes, that means here current from north to south, and the deflection is in the east or east way, and now we change the direction of current. Now the current flows from south to north. What happens to the direction of deflection? Now the direction of deflection changes to west. From this, you can get an idea that if the direction of current changes, then the direction of magnetic field produced also changes. When the direction of current changes, the direction of magnetic field produced also changes. Direction of magnetic field produced also changes when the direction of current changes. Now, how this magnetic field is produced? When current passes through a straight conductor, like this on straight conductor. See, this straight conductor, when current passes through it, how the magnetic field is producing here, that we want to find out. For that, arrange a straight conductor through a cardboard. See this cardboard. Through this, we arrange a straight conductor. And this connected to battery and plug key, and to regulate current we use a variable resistor, and it is called a rheostat, and we can use here an ammeter to measure current. At first spray some iron dust or iron fillings here over this. Now this, see, these are perpendicular. That means this wire is passing perpendicular to this plane of this cardboard. Now place it by using a salt sprinkler. We can spray some iron dust or iron fillings. Then switch on by putting this plug key here. And observe, that means when switch on, I will tap this cardboard some 2-3 times. Tap this cardboard here some 2-3 times and observe how the iron fillings arranging here, and observe how the iron fillings or iron dust arranging here. Now you can see these iron fillings are arranged in a concentric circles. Iron fillings now here arranged in concentric circles, and its curve increasing That means near this conducting wire, the iron fillings here, iron fillings are arranged here more, and its amount decreases, and also the curvature of the concentric circles increases. That we can observe. What it means, as moves from the center, the strength of the field gradually decreasing. Strength of the field is gradually decreasing. Now, the same things after removing this iron fillings, we can draw with a magnetic compass. That means when we place magnetic compass, its north pole points towards one end, and we mark it. We get the same circles by using this compass when we draw. So, the magnetic field produced here, we can represent by means of concentric circle. This direction of magnetic field can be obtained from Fleming's right hand rule. That means if the conductor is held with our right hand, see, the conductor is held with the right hand, then the thumb points the direction of current, then the fingers, you see, I am going to catch this on this direction. This is the direction of the magnetic field. This is the direction of magnetic field. So, the magnetic field produced here, we can find, that means the direction of the magnetic field produced here, we can find by using Fleming's right hand rule. Otherwise it is called what is a screw rule. That means when we screw, that means a right hand screw, if the tip at which the screw advances shows the direction of current, then the directional rotation of the screw gives the direction of the magnetic field. In this way, we can find the direction of magnetic field around a current carrying straight conductor. Okay? Now, what are the things we discussed today? We discussed about how a magnetic field produced when a current passes through a conductor. That means whenever current passes through a conductor, there will produce a magnetic field. We also discussed how we can find its direction. We can find the direction of the magnetic field, that is a magnetic lines of force, and its direction we can find by using Fleming's right hand rule in the case of a straight conductor. And the direction of the magnetic field is always from, but is outside the magnet is from north to south, and inside the magnet it is from south to north. Okay, with this all we can wind up today's class.